Alrighty, now everything's working. Sorry for the delay. I was working out a derivation to make sure that I could show you guys. And so today I'm going to be talking about the PHYS law and the magnetic field. And so let's see what we can do with it. Well, first off, I'm going to start with PHYS law. Now, PHYS law is defined as dB, or the change of the magnetic field, is equal to the magnetic constant mu naught times the current over mu naught I over 4 pi times dl, which that is your length vector, or how your length vector changes, crossed with r vector over the norm of r cubed. Now, normally, you might, if you guys are watching this, you might realize that, oh, this looks a little bit different than what you know. Well, if you notice, this term, the way it's probably introduced is dl cross r hat over r squared. Now, r hat is the unit vector, so it's just r divided by the norm of r. If I bring that downstairs down here, you get a cubed. So, nothing to worry about, guys. That's just something that, yeah, that's just a math trick. I did it for simplifying because it'll help out. And so, all right, let's start. If I give you a scenario where you have a wire like this, let's say that this is your wire, and you're looking for the magnetic field in a circle. It goes like this. Okay, so we can have our dl be the infinitesimal length of our wire. And we're looking for the magnetic field portion that's affected by this little length, similar to the electric field like what we derived earlier. And so we're looking at this projection to the magnetic field right here, dB. Correct? And so, if we're looking at this, we're trying to find the direction of the magnetic field. And what is the magnetic field in this case? Well, we'll also define this center right here to be a distance big R. Now, if you're confused on how this looks, because I drew it in 3 dimensions, this is your circle. This is your dl right here. And then here's your wire. This distance right here is big R. And so we're just talking about the distance from dl up to where this loop is. And so if my page will extend like I asked it to. And so now it gets our situation. We can set up our system to be dB is equal to mu naught I over 4 pi times dl cross r over the norm of r cubed. Once again, nothing to worry about with this r cubed. I just wrote it a little bit differently. And you'll see why, because I believe this way is much more useful and much more dynamic for you. If you see what this equation will result to, it's a little bit more clear on its applications. It makes it much more broad. And so, all right, well, we need to find out this cross product of dl cross r. Now, if you look over here, if you look right here, dl is a vector that only points in one direction. So I also forgot to go on our coordinate system. I'll do that in Greek. Let's say that this is x, this is y, and z comes out of the page. And so it would appear that the vector dl is actually composed of three components. Now it's only going in the y direction since the wires line up with the y-axis, right? That's what we set up. The wire right here is going directly along the y-axis. So because of that, we have our components 0, dl, the magnitude of dl, and 0. It doesn't go in the x, it doesn't go in the z, but it only goes in the y. That's great. Now, we need to find out what r is. Now, r is this hypotenuse. Here's your distance in x, and here's your distance in y. And so the r is your components in x and y. And since r points up and to the right, r points along b, or r points, r points to that red ring where we're trying to look for the magnetic field, then you'll see that r has components of x and y and none in z. Pretty neat stuff already. And so, and you might be thinking that x should be, or y should be negative, but if you look at the vector, it points up and to the right. Up and to the right means you have positive x and positive y. And that's just the way we defined it. And so we're just doing a general case. So if we do our cross product, cross r is equal to our x hat, y hat, z hat, which are 3 unit vectors. And then we're going to take the determinant of this, which is our components of dl, 0, dl, and 0, and then x, y, and 0. And so, if we take the determinant of this, you'll see that we have x hat. Since these are vectors, we want to get a vector. We want to get a vector as the result of this cross product. And so we have x hat. You cover up this end, and you take the determinant of these two, which is 0 minus 0. And then you take minus y hat times 0 times 0, which is 0 minus 0, plus z hat 0 minus x times dl. Perfect. And so that is our cross product right here. And that should make sense to us. You know, we know that dB is proportional to a cross product. Since the magnetic field is proportional to the cross product, dl cross r gives you a vector that's perpendicular to all 3 of them, or all 2 vectors, dl and dr. If this vector, the magnetic field, is in the z direction, which is defined by our answer then, be z hat, which means that, oh no, sorry, which means that, yes, our dl points in the y direction, our r points in the x and y direction, so then b must be perpendicular to both of those. So b should be in the z direction, just to make sure you're doing it correctly. And so we can write this now as d is equal to u naught I over 4 pi times dl u naught I times negative x dl. And this is the magnitude of dl. Good. Over. Now, let's consider this r cubed. It's the norm of r cubed. The norm of r is equal to the square root of x squared plus y squared. Hey, what's going on?
Hi. You're the only one here.
Yes, you are. So I was just rambling away about magnetic fields. So.
I have a question on the homework. I don't know how to start it.
Yeah, no, that's perfectly fine. So.
Yeah, I'm a little confused on that. I realized I couldn't do it after staring at it for like half an hour and going, nope, I don't know what I'm doing.
That's okay. It's not as bad as me. I was doing a problem in physics, and I kept getting a result that was, I didn't know how to solve it, and then I didn't read the problem correctly. And
Right.
it simplified perfectly into like an answer that took like 2 minutes. So, so don't worry about it.
Yeah, so I don't know exactly how to start it. See, I looked at the videos and it has something like that, but it's giving me the angles, but it's given the form like that, so I have to, I'm not sure.
Okay, so your scenario is like you have this triangle loop, right?
Right.
Okay, and so a wire is formed in the shape of. Okay, what are you trying to find?
I'm trying to find the work.
Oh, the work you do. Okay. And so it says this is scenario 1,
Right.
and then this is scenario 2.
Correct.
Okay. Okay. So first of all, you know that. What do you think the work's going to be? First of all, based on what you have.
What do you want? What do you like?
So usually work is the opposite of potential, right?
Mhm.
And things with the lowest potential means that it's going to move the way it wants it to. And so if you look at mu naught, just before we solve anything, like if you look at mu naught, which is the direction this is going, and you curl your fingers up, your moment points out of the page, right? So that's perfectly anti-parallel to your magnetic field, right?
Right.
That means that it's going to want to lower its potential. The way it lowers its potential is if they're in the same direction, right?
Right.
Because it's negative mu dot b. If the angle is 0, then you get a negative value. And so it's going to want to move towards that way, right?
Mhm.
So it's going to want to do work, and it's going to do it in a way where, yeah, it's going to point out like this.
Okay.
Because the magnetic moment ends up pointing in the same direction, right?
Right.
Okay, so the work from going to here is equal to you remember the work is equal to, if you're talking about torque, since torque is measuring in radians,
Right.
it's torque, it's the integral of torque with respect to theta, and theta is how many radians you go through.
Right.
So if you define your first situation to be 0 radians, and your last situation to be, so it's going completely flipped. Yeah, it's going completely flipped, 180, right?
Right.
So you're going from 0 to pi radians, right?
Right.
You'll just need to know what the torque is. And then the torque is equal to, oh, do you know what it's equal to? So it's a vector, right? And it's always perpendicular to the magnetic moment and the B field. So it's mu cross B, right?
Right.
Where mu is equal to n for the number of loops you have, I, times your area vector. So what I was doing before with curling my fingers,
Right.
that's what it is. Your current is going like this, and it's going counterclockwise, right?
Right.
If you curl your fingers like this, what's perpendicular to that is your thumb, and your thumb is where mu points,
Okay.
and that's the same as your area vector, right?
Right.
Okay, so, all right, so that's your torque, and your torque will be, it will be If you're just looking for the magnitude, it'd be mu b sine theta, right?
Right.
And so if you put this in here, you have 0 to pi over 2, or sorry, 0 to pi. And then you have mu b, right?
Right.
And then you integrate it. And then you integrate it. What's the integral of sine? Negative cosine theta pi to 0. And since you actually moved 180 degrees, I mean, you're just doubling your potential. So then this will end up being minus, if I take out the mu b, minus a negative 1, minus 1 times 1, right? Which is 2. Right?
Right.
Does that make sense?
Mm-hmm.
And if you have a positive work, that means you want to move towards the direction where its potential is lowest, right? And since potential is the opposite of that, if you worked it out, it'd be negative for the potential. So, yeah, and then the work would just be simply that, since you're moving 180 degrees. So, but the only things you need to actually figure out are what's mu, and it probably already gave you the B field. Right?
Yeah, it gave me the B, what was it?
The current.
Current.
Right, and then you just need to find the area then. So the area of a triangle is what? 1/2 base times height.
Right.
Right, yeah, and that's it. Does that make sense?
When you said the 180 part, is that just a given? You're gonna.
So that's kind of based on what I was explaining to you.
Right,
So if you look at your moment right here, and once again, if you curl your fingers in the way the current's going, wherever your thumb points is where your moment is. So they're perfectly perpendicular like this, right?
Right.
In the last situation, if you do it, they're both in the same direction, right?
Mm-hmm.
So that means you move from here to here, right?
Right.
That means you move from 0 radians to pi radians, right?
Right.
So the work, when you're doing that, when you're integrating, you're going from no radians to move pi radians, right?
Right.
And then you know that the cross product is actually sine theta, or proportional to it, so you have some way you can integrate it.
Right.
Does that make sense?
Mm-hmm.
Yeah, and so, yeah, and then you just need to find the area of the thing.
Okay, yeah, because in the, like, I saw the video and they had something like that where it's giving all of that, and I wasn't sure exactly.
Right. No, I totally get you.
Yeah, because then it was giving me like cosine, like, you would use cosine, an angle, was minus.
So you can, like I said, the work is always the opposite of the potential, right?
Right.
Now you can do it like this if you're really snazzy. Your beginning situation, you know that you had a high potential, right? U initial is equal to negative mu b cosine theta. It's really mu dot b, but then the dot product's cosine. So first of all, you're anti-parallel, right? So the angle is 180. Mu b cosine theta is equal to, or cosine of pi is equal to positive mu b, right?
Right.
And then u final is equal to negative mu b cosine of 0, since they're both in the same direction.
Mm-hmm.
That equals negative mu b. So the change of potential from going there to there is equal to final minus initial right?
Right.
Is equal to the opposite of work. Right?
Right.
So you could do it using this, knowing your potentials. And you just take the difference of the two at the two different angles. Or you can integrate it out. If you really want to be very precise, you can integrate it since it's continuous and say, oh, hey, the opposite of this is your potential. Well, yeah, that's true, right?
Right.
Does that make sense? So you can do it both ways. whichever way works best.
Oh, yeah.
But once again, sometimes you might not have that in your situation. You might be like perfectly perpendicular, and then you have to move just 90 degrees or something.
Okay.
So there might be a problem, if I remember correctly when I took this class, that the thing was actually perfectly up, and it asks you for the work when it moves down at 90 degrees, which then you just integrate from 90 or 0 to pi over 2, right?
Right.
Which is, yeah, so does that make sense?
It does. It does. Yeah, because I wasn't sure exactly. I was a little confused, to be honest. I was like, I don't know what it's doing.
No, that's okay. Don't sweat it. But is that clear on why that works out like that?
Yeah, it definitely does. Like I said, I was a bit confused as to why they were doing the cosine minus the angles, but now, I mean.
Right. Yeah, and it just, basically the way it is just because you define your potential to be with respect to the magnetic field. And so it's the dot product for that, or the torque is the cross product for that on how it moves perpendicular to it. And so, yeah, I mean, I don't know, it doesn't seem as bad when you like break it down like this.
Right. Is that what you were talking about before I came in?
Kind of. I was talking about actually the magnetic fields. Did you guys talk about Ampere's law, or did it for your pre-lecture? The thing with the loop and the magnetic field around a wire.
That's for the pre-lecture.
Right. Yeah. So you derive it from Biot-Savart's law, but you can also derive it from, or you could also derive Ampere's law from that too. And so I was just showing how to do that, but that's okay. So.
Were you also doing chemistry over there?
No, not me. No.
Okay, I was like,
No.
How does that tie in with physics then?
Yeah, it looks like some equilibrium reactions, but.
Yes. It looks like some basic chemistry. I like that.
But do you have any other questions on anything?
Where are you usually available?
Always this time and Wednesdays.
It's just Wednesdays and.
It's Mondays and Wednesdays.
Okay.
So it's here. I did it during the lunch because I know a lot of people are, me and a lot of people are busy throughout the day.
Right.
And I also commute, so I can't really stay here and do sessions like in the evening.
Yeah.
And so everyone's free during lunch.
Yeah. Okay.
Or if you want to be free during lunch, you grab your food and
Just come in here and be like, what?
People come in here and eat, so.
Or for our next exam, are you gonna give another?
Yeah, of course.
Okay.
Yeah, totally. I believe there were 3 kids that showed up for the exam review, and which was very nice because having such a low number, you can like work one-on-one with people. So, like you see, there's a lot of people in this room, so it's much easier to work with a person one-on-one than sometimes explaining generally, because people got questions from everywhere.
Right.
So,
Okay.
but yeah, I'm always here, so maybe also email me too if you need any questions.
Yeah, I wasn't sure if you could email you still. I was like,
Yeah, of course. I mean, yeah, that's why my email's out there.
Okay.
So,
Sounds good.
yeah. So is that it?
Yes, I have.
Would you just mind signing this? So, just your number and your name.
I don't have my ID. I think look it up though.
That's okay. Yeah, I'll have it on when I actually log you in.
I don't have my ID, or do you want me to look it up?
No, it's okay
You're
because
good?
I'll just. Yeah, no, it's fine.
Yeah, well,
Or I can just ask you tomorrow or something.
I'll have it tomorrow.
Yeah, then that's whatever floats your boat. But yeah, once again, is that clear and stuff?
It is.
So-
a lot more.
So whatever I do is I actually post these online, so if you're ever curious to see what I'm talking about, even if there aren't people here, you'll see that I'll do something that has a title, and then, but if there are people here, you'll see like an interruption. So the interruption's that line. But yeah, they're free and available for you guys.
Do you post these on Blackboard or on?
They're on Blackboard.
Okay. Okay.
Yeah, they're on Blackboard. So
Sounds good then.
yeah, no problem.
Thank you.
Yeah, so, no problem. Bye, see you later. And so yeah, if we come back to up here, we'll see that we can substitute back to our equation. We get dV is equal to mu naught I over 4 pi. Remember, we have x dl over, now we have the square root of x squared plus y squared cubed for the norm. Now, why I said that this is very convenient is for the following reason. If we integrate this out, we can solve for the magnetic field and find a general form. B is equal to mu naught I over 4 pi, pull out the constants, and I'm going to say, and I'm going to change coordinates for x. And so, or I'm going to change coordinates for dl. So, if we say x is r cosine theta, which we define big R as to be that distance, we can see that we have integral u naught I r cosine theta, and you can go from you can change your dl to be proportional to you set dl to be proportional to is equal to r d theta, because this is an arc. If you look up here, our scenario, our dl gives us an arc with an angle between the 2 points. And so we can multiply this by another r d theta over square root of x squared plus y squared cubed. Now, you're wondering, why didn't I change the x on the bottom? Well, I'll tell you why. If you want to do it numerically, for x equals 0, if we see that x equals 0 just gives us the ring, gives us the magnetic field of the ring, at x equals 0 we have just the B field, or the ring, or the circle up there. And so if we set x equal to 0, and we set y equal to r, since y is actually our distance from dl, and this length right here is r, to give us where x is equal to 0, hold on, I said it backwards. At x equals 0, oh no, I didn't. At x equals 0, you want to be at the origin. You want to find the B field around the origin, because that's where the ring is perfectly symmetric. So we set x equals to 0 and y equal to r, because that gives us that length that we defined up here, where y goes from dl to r. And so we can get b is equal to mu naught I over 4 pi integral r squared over, now at x equals 0, this term goes 0, and y equals r, this term becomes r squared square root to the cubed, which is equal to r cubed. and we have an r cubed here, which will cancel out to just r times cosine theta d theta. I forgot, I left out my minus sign upstairs. There's a minus sign from the cross product. So I forgot my minus sign, which is my apologies. The integral of cosine is actually negative sign. We have a negative right here, and we're going to be integrating from 0, not from 0, but from minus pi over 2 to pi over 2. Because if we look at our range of theta, theta goes from here out at infinity. At infinity, we have our magnetic field ring to be exactly pi over 2 or 90 degrees apart. The same thing at minus infinity. That will be the same thing. You'll have a wide enough circle where you have everything to be 90 degrees apart. And so that's our bounds of integration. Integral of negative cosine and sine, or integral of negative cosine is actually negative sine. And so we have negative mu naught I over 4 pi r times cosine of pi over 2 is 1, minus sine of negative pi over 2 is minus 1, which gives us negative mu naught I over, this value becomes 2, and we get 2 pi r. Now, the reason why it's negative is because we have the vector b. And our negative sign tacks on a z direction, which we solved for before. When we did our cross product, we had the b field going in the z direction, in the negative z direction, to be honest, because of this negative sign. And so, if you tack on a negative z direction, you'll see the b field goes there. And that's perfectly true, because you know that if you have a wire like this, you had a wire going in the y direction, you know that if you curl your fingers around in a circle like this, and if current goes up like this, I goes up in the y direction, and you curl your fingers around, you know that the b field has to be where you curl your fingers around. Well, wherever you curl your fingers around, at this point right here, the b field points into the page. B is equal to bz in the negative direction, because our z direction here is positive z. This goes to negative z. And so going into the page in this scenario means our b field is in the negative z direction, which corresponds to what we solve for analytically. So everything is good. And once again, if you guys are learning, since you guys probably have started Ampere's law, you have the b field is equal to integral around a closed loop mu naught equals it's mu naught b. Gave the answer out. It's b dot dl is equal to mu naught I. And so, if you look at in our scenario, if you say that these two things go in the same direction, which if we draw a circle around a wire, the b field goes into this direction, goes into the same direction as our circle, which means that we can write this as B times 2 pi r. Since the dot product of the two gives you a scalar, we have the magnitude of B and the magnitude of our closed loop. And so we have that is equal to mu naught I, always for any loop. And I is this current here, and we're looking for the loop to close. And so B is therefore equal to mu naught I over 2 pi r. And we know that that's the same value as what we saw for above. Using Biot-Savart's law, and you get Ampere's law as a consequence from it. Likewise, you could use Ampere's law to deduce what the magnetic field is for a case where you have a loop going around a circle. And once again, that proves that the Biot-Savart's law was actually explained experimentally. And this Ampere's law was designed to explain what that meant in a general case. And so you would expect these two answers to be the same in a case like that, which is very true. And so if you look at Biot-Savart's law, what's very nice about it is because if you construct it correctly, this square root will tell you the distance between any point you want in space. Likewise, these bounds of integrations for these angles, or for whatever transformation you do, in this case we transform with respect to theta, then you should get that, yeah, those are, yeah, you should get that those would give you a certain magnetic field based on the scenario you have. And it works out that, yeah, if you take your general equations correctly and you do your cross products correctly, then you should get a general form for the magnetic field. And if you did it in a case where you have a circle and everything is nice and symmetric, you have the same magnetic field as you would expect using Ampere's law.